Okay, this lecture is energy level diagrams, which is part of modern physics. And basically, I'm going to be talking about atoms absorbing photons and atoms emitting photons. So this is an overview here. On the left, I have a picture that's showing absorption, and on the right, emission. So on the left, you can see this is a Bohr model representation of an atom. I have the nucleus in the middle, and the concentric circles represent different orbits or energy levels of the electron. On the absorption side at the top, the squiggly orange arrow is showing an incoming photon. It's absorbed by the atom. The electron, which is in the first circle, jumps up to the third circular orbit because of the energy from the incoming photon, which has been absorbed. And at the bottom of the same picture, I have a red arrow coming in. This is another incoming photon. It has a larger wavelength, thereby lower frequency and less energy. That photon is also absorbed by the atom, and that electron is jumping from the second energy level to the third. On the right, we have emission, which is kind of the opposite. At the top of the diagram, we have an electron that's falling from the third energy level down to the first, and it's giving off a higher energy photon. At the bottom of the picture, we have an electron that's falling also from the third energy level, but it's only falling down to the second, and it's giving off the red arrow, which represents a lower energy photon. Absorption, absorbing incoming photons. Emission, giving off photons. So I wrote here, this is a different graphical representation of an atom's electron falling to a lower energy level and emitting light. So in the lower left-hand corner of this graphic, there's the Rutherford model of the atom, central nucleus, and these electrons that are zipping around outside of it. The two larger pink ovals represent these energy levels of a specific electron. At the top, it says an electron at a high energy level, and then that falls down, and we have an electron at the lower energy level. And when it drops from the higher level to the lower level, a change in energy levels releases light energy. So this graphic here is from the physics reference table. This is showing the energy levels of a hydrogen atom and the energy levels of a mercury atom. We need to understand and obtain data from these diagrams. The diagrams show the energy associated with electron orbits in both a hydrogen atom and a mercury atom. So looking at hydrogen, at the bottom we have n equals 1, that's the ground state, and that has negative 13.6 electron volts associated with it. What that means is if I wanted to make this hydrogen atom an ion, if I wanted to completely remove that electron, it would take 13.6 electron volts of energy to do that. I then have the other energy levels, N2, N3, N4, and so on. At the top, it says N equals infinity. That's ionization. At that point, the electron's gotten further away from the nucleus so that it's just gone forever. So that hydrogen atom now becomes an ion because it lost the electron. If I had an electron that was falling, for example, falling from the n equals 2 to the n equals 1, I would subtract those two energy values, 13.6 and 3.4, and that's how much energy the electron would lose as it falls. And that would be equal to the energy of the emitted photon. To the right, I have a mercury atom. Now this one doesn't say N1, N2, N3. Instead, it has letters. And underneath it, it's captioned a few energy levels for the mercury atom. So I think there are more energy levels that are shown. This is why they're not numbering it. Instead, they're going to letter it. But it's the exact same idea. The lowest energy level is the ground state. And then at the top, it's showing the point at which the electron leaves, or ionization. So if an electron were to move from, say, E to A, and I want to know the change in energy, I would just subtract the number associated with E and the number associated with A. So we're going to do a few examples in a moment. And this slide here, I'm just showing you that on the left, we're back to our graphical representation of an atom. The nucleus in the middle, the concentric circles represent N1, N2, and N3 energy levels. On the right, we have the chart from the reference table with N1, N2, N3 as well, and we can read how much energy there is associated with each from the chart in electron volts. The picture on the left has this green electron. It's falling from the N2 to the N1, and then it's giving off that squiggly cyan colored arrow. It's giving off a photon, and E equals HF is the energy we would use if we wanted to find the frequency. So I wrote, notice the N equals 1 on the chart is the first ground state electron orbit. Notice each energy level has an energy in electron volts. And ionization means the electron has left the atom, making that atom an ion. So here's the first example. I have the same picture to the left, and again, the hydrogen chart from the reference table. An electron in the N2 orbit falls to the N1 orbit. How much energy is lost? So on the left, we see the green electron is falling from N2 to N1 and giving off a photon. So what we want to do is go to our chart on the right and subtract the energy values for N2 and N1. So I wrote 3.40 electron volts, N2, minus negative 13.60 electron volts, that's N equals 1. That difference is 10.2 electron volts. Now in this problem, we ultimately want to find the frequency, so we're going to convert that into joules. To convert into joules, at the bottom of the page, I have 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. So I'm going to take my answer, 10.2 electron volts, multiplied by 1.6 times 10 to the negative 19th, and I get about 1.6 times 10 to the 18th joules. That's how much energy that electron lost when it fell from N2 to N1. Now I'm asking, what is the frequency of the emitted photon? I'm going to use the formula E is equal to HF. For E, I'm going to put in the energy of the electron in joules, and that's equal to Planck's constant, given at the bottom of the page, times F. I'm going to solve it for F by dividing both sides by Planck's constant, and the frequency comes out to be 2.47 times 10 to the 15th hertz. Remember, frequency is measured in hertz. I'm now asking what type of radiation this is. So we have to look up the electromagnetic spectrum from the chart, which is on the next slide. So we want to find 2.47 times 10 to the 15th hertz on the chart. So frequency is on the bottom here. And times 10 to the 15th is just to the left of visible light. So this frequency is just beyond violet. It ends up in the ultraviolet range. So the photon that's emitted would be ultraviolet radiation. So let's look at another example. This example is going to ask us wavelength. So it uses the other formula for energy of a photon. An electron in a hydrogen atom drops from the N3 to N2 state. Determine the energy of the emitted radiation. So I'm going to look at how much energy there is at N3 and how much energy there is at N2 and subtract the two. Subtracting those values, I get 1.89 electron volts. Now it asks, what is the wavelength of the emitted radiation? So instead of E equals HF, we're going to use this version of the formula. E is equal to HC over lambda. Solving that for wavelength, I get wavelength is HC over energy. H is Planck's constant. C is the speed of light. In the denominator, we have the energy, 1.89 electron volts, and I'm multiplying that by my conversion factor, 1.6 times 10 to the negative 19th, because I need joules. And this answer comes out to be 6.56 times 10 to the negative 7th meters. Wavelength is a distance, so the units are meters. So, more questions for the hydrogen atom chart. A hydrogen atom emits a 2.55 electron volt photon as its electron changes from one energy level to another. Express the energy of this emitted photon in joules. We have to use the conversion factor. Determine the frequency of the emitted photon. We have to use E is equal to HF. And use the chart to determine the energy levels. So where on this chart is there a difference of 2.55 electron volts? So the next slide has the answers. The first bulleted point says, express the energy of the emitted photons in joules. So I'm going to take 2.55 electron volts, multiply it by the conversion factor, I get the energy in joules. Next bulleted point says, determine the frequency of the emitted photon. I use E is equal to HF, and I can solve that for the frequency in hertz. The last one says, determine the energy level change for the electron. So this is a tough one. We have to use trial and error to figure out which change in energy levels can give us 2.55 electron volts. So you just start subtracting those numbers from each other until you can find 2.55 electron volts. So it turns out that N4 to N2 is 3.4 minus 0.85, or exactly 2.55 electron volts. So when the electron falls from N4 to N2, it releases exactly 2.55 electron volts, and that's what we're looking for. So the answer is 4 to 2. So here we have an example that's using the mercury atom chart, and I asked it all at once, but then I gave the solution in these 4 different steps. An electron in a mercury atom falls from the E to the B levels. What type of radiation is emitted? So the E level, you can see energy associated with E is negative 3.71. And the B level, the energy associated with that is negative 5.74. So step 1, find the energy difference. I'm going to subtract those two. Step 2, convert to joules. So I'm going to multiply the answer by the conversion factor. Step 3, calculate the frequency. I'm going to use E equals HF and solve it for F. So I get this final frequency. Step 4 is to look up that frequency in the chart. So on the right here, I have the chart from the physics reference tables. On the top, it has wavelength, and on the bottom, it has frequencies. This frequency is 4.82 times 10 to the 14th. So if I look at my chart, times 10 to the 14th, that's near the visible light. If I look at the colors of the visible light, looks like this guy falls exactly at the end of orange, or in between orange and red. So I wrote orange light, or between orange and red. So just a reminder from the beginning of this presentation, there's absorption. That's when it causes the electron to jump up. And then there's emission. That's when the electron falls down. So I wrote, incoming photon can be absorbed by the atom, forcing the electron to jump to a new energy level. Or it can be emission. When the electron falls back down, a photon is given off. So let's look at another problem here. What radiation is required to ionize hydrogen when the electron is originally in the ground state? So in other words, the electron's at N equals 1. That has 13.6 electron volts associated with it. And energy is going to come in and excite that electron all the way up to the N equals infinity. So step 1, find the energy from the chart that ionization requires. So if it's going from 13.6 and at the top it says 0, that changes 13.6 electron volts. Step 2, convert into joules. So multiply it by the conversion factor. Step 3, find the frequency. E is equal to HF. And lastly, find the radiation type from the electromagnetic spectrum chart. So looking at the chart, if our frequency is 3.28 times 10 to the 15th, 10 to the 15th is in the ultraviolet. But really, the answer is not just ultraviolet. Ultraviolet or anything higher will cause that electron to be ionized. So ultraviolet is the lowest amount of energy, but X-rays and gamma rays would also work. Okay, so I want you guys to complete the worksheet as best you can. I will have another video giving some help on the worksheet, but do your best to complete that and upload that to the portal before the due date.